Hi, this is Dr. Habib, and today we will talk about ion implantation. Before going into the details of ion implantation, let's have a refresher of the basic concepts of semiconductor bonding, especially bonding in silicon, and let us talk about the N and P type doping of silicon using phosphorus and boron. So we know that silicon has an atomic number of 14, where it has 2 electrons in the first shell, 8 electrons in the second shell, and 4 electrons in the outermost shell. So silicon shares its outermost shell electrons with 4 neighboring silicon atoms, resulting in covalent bonding. Now we know that at absolute zero temperature or 0 Kelvin, all these electrons are attached to the parent silicon atoms. Or by analogy of a semiconductor band gap, we can say that the valence band is full of electrons and the conduction energy level is empty of electrons. Now if we slightly increase the temperature above 0 Kelvin, some of these electrons gain enough kinetic energy to break this bond, and now they are freely available to move around inside the semiconductor. By analogy, we can say that an electron has transitioned from the valence energy level to the conduction energy level. And then when we bias the semiconductor, we direct the flow of these electrons in holes. So the electrons are attracted towards the positive terminal and the holes are attracted towards the negative terminal. We know that at room temperature for each kind of semiconductor, depending on the band gap, we have a particular carrier concentration, a particular number of electrons per centimeter cube and holes per centimeter cube. For silicon, which has a band gap of approximately 1.1 electron volts, this intrinsic carrier concentration is approximately 1 into 10 to the power of 10 per centimeter cube, which means that at room temperature we have 10 to the power of 10 electrons and 10 to the power of 10 holes available for conduction inside silicon. This number, intrinsic carrier concentration, is a function of temperature and it's a function of the band gap. It increases with temperature and it's inversely proportional to the band gap of the semiconductor. With increase in the band gap of the semiconductor, the intrinsic carrier concentration decreases. Based on the band gap of the semiconductor, we can classify materials into conductors, semiconductors, and insulators. In conductors, the valence band and conduction energy level, they overlap. So we have plenty of electrons available for conduction. In semiconductor, we have a band gap. For example, it's 0.66 for germanium, 1.12 for silicon, 1.42 for gallium arsenide, 3.4 for gallium nitride. For insulators, this energy band gap is really wide. So it's almost impossible for electrons to jump from the valence energy level to the conduction energy level. And that's why insulators do not easily allow the flow of current and heat through it. Now let us talk about the doping of semiconductors, particularly about the doping of silicon. We know that in case of silicon, the intrinsic carrier concentration is 10 to the power of 10 per centimeter cube, which means that we have 10 to the power of 10 electrons and 10 to the power of 10 holes available for conduction for an undoped silicon material. But is that number enough for making devices for conduction? The answer is no. We need doping levels of the order of 10 to the power of 15, 10 to the power of 16, 10 to the power of 17, 10 to the power of 18, 19 per centimeter cube in order to make devices like solar cells, LEDs, photodetectors, lasers, transistors, etc. So we have donors and we have acceptors. We need pentavalent impurity for n-type doping of silicon. For example, phosphorus, it has 5 electrons in its outermost shell. 4 of its outermost shell electrons make bond with the neighboring silicon atoms, and the 5th electron is loosely bound to the nucleus of the phosphorus. And with the slightest amount of energy, for example at room temperature, at thermal energy, this electron can easily flow inside the semiconductor. It's called free electron. So by analogy, we can say that n-type doping means that we introduce donor energy levels close to the conduction energy level of a semiconductor. Since this gap is really small, for example, for n-type doping of silicon, it's of the order of 25 to 30 millielectron volts. So even at room temperature, all the electrons transition from the donor energy levels to the conduction energy level, and they are available for conduction. Similarly, for p-type doping of silicon, we need boron or trivalent impurity, for example, boron, aluminum, indium, etc. Boron is the most common p-type dopant in silicon. It has 3 electrons in its outermost shell. These 3 electrons make bonds with the neighboring silicon atoms. But then over here, we actually have a missing link. We have an absence of electron. And we know in semiconductors that an absence of electrons is called a hole. So basically, by p-type doping, we actually introduce holes into the semiconductor. Then this hole can also move around inside the semiconductor. I don't want to go into the details of it. I have already discussed it in one of the previous lectures. By analogy, we can say that p-type doping means that we introduce acceptor energy levels close to the valence band of the semiconductor. So at room temperature, electrons jump or transition from the valence energy level into the acceptor energy level, leaving behind holes. And in semiconductors, for the flow of current, we either need free electrons in the conduction energy level, or holes available in the valence energy level, or the combination of both. Now let us talk about the ion implantation. So I discussed the p-type doping of silicon, for which we need trivalent impurity, and the n-type doping of silicon, for which we need pentavalent impurity. But now the question is, how do we dope the silicon material with n and p-type impurities? So there are several techniques in order to do that, and one of the techniques is called ion implantation. So basically, we need to do two things. We need to add dopants into the semiconductor, and then we need to make sure that the dopants are activated. In order to donate electrons or holes to the semiconductor, we need these dopant atoms to settle down on proper lattice sites. If they do not sit on the proper lattice sites, they do not contribute electrons or holes to the host semiconductor material. So it's really crucial to activate the dopants. So the first step is to add dopants, and the second step is to activate the dopants inside the semiconductor. And ion implantation also performs the same functionalities. So ion implantation is a low temperature technique for the introduction of impurities into semiconductors via the bombardment of the surface of the host atom with high energy ions. For example, consider a silicon crystal lattice, where inside the crystal lattice, or inside the substrate, or we can also call it the wafer, we have periodic arrangement of atoms over here, as you can see. Now we introduce high energy dopant ions. These could be borons for p-type doping or phosphorus for n-type doping of the silicon substrate. These high energy ions hit the substrate material at really high energies, and when they hit the host silicon atoms with high energies, they knock off the silicon atoms from their lattice sites. And these high energy ions can actually travel inside the host material down to a certain depth. The depth of the implanted ions is defined by the energy. The higher the energy, the deeper these implanted ions can travel inside the host material. So, since the implanted ions have high energies, they knock off the host atoms from their lattice sites. They introduce damage into the semiconductor crystal lattice, and it leaves the substrate amorphous close to the surface. As you can see over here, that it dislodges the silicon atoms from their respective lattice sites, resulting in an amorphous layer close to the top surface. But below that, we would still have periodic arrangement of atoms. So when it introduces damage close to the surface, it results in defects like vacancies, interstitials, divervacancies, or dislocations, which are actually clusters of point defects, line defects, for example, dislocations, that kind of stuff. Now, in order to recover from the damage and also to activate the dopants, we need to perform annealing to restore the lattice and also to activate the dopants on proper substitutional lattice sites. Annealing is actually a high temperature technique which is performed for a particular amount of time. For example, consider the crystal lattice once again. Assume these are the this is the periodic arrangement of silicon atoms inside the wafer. We introduce high energy implanted ions into this crystal lattice. These ions dislodge the silicon atoms close to the surface from their lattice sites. So now this layer over here, which is close to the top surface, becomes amorphous. So we perform annealing of the wafer. Annealing actually is a high temperature technique in the range of 950 to 1150 degrees C for 30 to 90 minutes for the activation of the dopants. So annealing provides energy, like these high energy ions, when they enter the surface, they start losing energy, eventually settling down, kind of stopping. In the end, at the end of the day, they are just left with the thermal energy, which is around 26 millielectron volts. But once we heat up the wafer at these high temperatures, these atoms gain thermal energy once again. So they start moving around. They start moving around and they try to find the lattice sites. Once they find the lattice sites, they just settle down over there. So the damage is recovered, and also these dopants are activated at various lattice sites. Here is the block diagram of ion implantation. So initially we need a source of ions. And how do we generate that source of ions? We actually have a tube. We introduce a low pressure gas inside the tube, which has a mixture of the dopant atoms plus some other gases, and we introduce electrodes, cathode and anode, inside the tube, apply voltage to the electrodes, resulting in current flowing through this cathode, which is in the form of a filament. For example, you might have seen an electrical heater which is in the form of a helical spring, in the form of a filament. So we keep increasing the voltage until we arrive at the striking voltage, where this filament starts emitting high energy electrons, and these high energy electrons excuse me these high energy electrons they strike the neutral atoms and molecules, knocking off secondary electrons from these neutral atoms, resulting in ions. And then these electrons further knock off more number of electrons from more atoms and molecules. So actually inside this tube we have an environment of electrons and ions, and also neutral atoms and molecules. Like, not all the atoms and molecules are going to be ionized. Some get ionized and the rest are not ionized. So we have a plasma, which is a combination of electrons, positive and negative ions, and neutral atoms and molecules. Once we generate the plasma, the ions are pumped and directed towards an analyzing magnet. An analyzing magnet performs the function of a mass separator. It allows the intended dopants to pass through the magnet, and it blocks the unintended ions so that they are not introduced into the wafer. And after the analyzing magnet, we introduce the intrinsic, we pass the intended ions through an accelerator to increase their energy levels, and then we focus them and they get scanned onto the wafer, which is held by a Faraday cup, attracting these ions towards the surface of the wafer. This plasma actually has different colors depending on the gas type. For example, here is a plasma enhanced chemical vapor deposition equipment here at our Center for Advanced Electronics and Photovoltaic Engineering. And I was performing an experiment where I introduced argon gas into this tube over here, and then I started increasing the plasma power unless I arrived at a point where the plasma got lit. And here you can see the color of the argon plasma over here. Different gases have different colors. Oxygen, nitrogen has different kind of colors as compared to the argon plasma. The ion implantation could be non-selective or it could be selective. In selective ion implantation, we have the analyzing magnet, which allows the intended ions to travel towards the wafer, and it directs the unintended ions into some different direction, or it blocks it. In a non-selective ion implantation setup, we don't have the analyzing magnet, so it's not selective. Both the intended and unintended ions actually travel towards the wafer and get inserted into the wafer. We also need implantation masking for selective ion implantation. For example, talking about MOSFETs, where we have a substrate material which is also called the bulk region, which is lightly doped, and then we need to introduce a drain and a source region. We introduce the drain in the source region using ion implantation, but for that purpose we also need to cover the rest of the device. We need to protect the rest of the device either using photoresist or using silicon dioxide. There is a ion stopping process as well. We know that initially when these ions they enter the surface of the wafer, they have high energies. When they enter the substrate material, they start striking the atoms of the substrate material and start losing energy. Like, for example, initially this could be in kilo electron volts or hundreds of kilo electron volts, in the range of 5 kilo electron volts to approximately 10 mega electron volts, depending on the application. Once these ions enter the surface of the material, they start losing energy, eventually coming down to a point where they kind of become stationary. They are only left with the thermal energy of the order of 26 millielectron volts. Also, these implanted ions have a certain depth profile as a function of the distance. Like here we have the surface. If we plot the concentration of the implanted ions versus depth, where this point over here represents the surface, they have a particular distribution. They have a Gaussian distribution. They have a peak concentration at certain distance from the top surface, lower concentration below that, and lower concentration above that as well. So they have Gaussian distribution of the implanted ions inside the wafer or the substrate material. Here is the Monte Carlo simulation of the ion implantation, and we can see that the distribution of these implanted ions. The point where we see the peak distribution, the distance from that point to the surface is called the projected range. Then the distribution around the projected range in line with the direction of the ion implantation is called the projected straggle, and the distribution lateral or perpendicular to the direction of the ion implantation is called the transverse straggle. Excuse me. This figure over here represents the same phenomena: projected range, the transverse straggle, and the projected straggle. Excuse me. We already discussed that in ion implantation we have high energy ions. They hit the substrate material, and with the passage of time they start losing energy. With losing energy, they come to a stopping point. There are two stopping mechanisms in ion implantation. One mechanism is called nuclear stopping, and the other mechanism is called electronic stopping. Nuclear stopping occurs in heavier ions. For example, arsenic, which has an atomic number of 33 and atomic mass of 75. When it hits the host silicon atom at high energy, it displaces the host atom from its lattice site and either replaces its position or results in an amorphous surface. The other kind of stopping is called electronic stopping, and this mechanism occurs in lightly doped materials, in light ions, in lighter ions, for example boron or hydrogen. So the lighter ions, when they enter the substrate, they actually encounter a force of attraction with the clouds of electrons that are available inside the host material. These electrons apply a force of attraction on the ions, so with the passage of time these ions are going to keep losing and losing energy. And lighter atoms, by the way, travel deeper into the substrate material as compared to heavier ions, because heavier ions encounters collisions with the host materials. We can see that phenomena over here, that lighter ions like hydrogen and boron, they travel deeper into the substrate material, while heavier ions, for example arsenic, travel shallower into the substrate material. Advantages of ion implantation. One advantage of ion implantation is that we have precise control of dose and depth profile in ion implantation. For example, one application of ion implantation is a MOSFET, in which we need to implant the drain and the source regions in order to achieve heavily doped regions over here. And it's really crucial to have precise control of the drain and the source region, of the depth of the drain and the source regions, and also the carrier concentration. The distance between the drain and the source is called the channel length, or it is also called the technology node, and it's really crucial in technologies as well, because our technologies in processors and memories are based on complementary metal oxide semiconductors, in which we have p-type MOSFETs and n-type MOSFETs placed side by side. And the technology node actually is the distance between the drain and the source. The smaller the technology node or the channel length, the more number of transistors we can fit on the same size chip. So that's why you see that every newer technology has a shorter channel length, resulting in fitting more number of transistors on the same size chip, leading to higher speed and larger memories of the electronics. So that's why you see that your smartphones, their size does not really vary a lot from one technology to another, but their functionalities like speed and memory, they are increased. All of this happens because companies, they like Taiwan Semiconductor Manufacturing Corporation, Intel, etc., they try to reduce this channel length, fitting billions and billions of transistors on a single chip, resulting in increased functionalities of the electronics that we see. So for this purpose, ion implantation achieves precise control of dose and depth. It is fast as well, does not take a lot of time. We have a wide selection of masking materials, for example, photoresist, oxide, polysilicon, etc. It is less sensitive to surface cleaning procedures. Fabrication of electronics, LEDs, solar cells, photodetectors, lasers, transistors, diodes, etc., power devices, they have to encounter through, they go through a lot of cleaning procedures, chemical cleaning and physical cleaning procedures. And since in ion implantation, the peak carrier concentration is at a distance way below the surface, and the cleaning procedures mostly affect the surface only. So cleaning procedures do not affect ion implantation. Also, ion implantation results in excellent lateral uniformity, which is also crucial for consistency in electronics. There are some disadvantages of ion implantation as well. The annealing recovers partial damage, but it does not recover all the damage introduced by the ion implantation. Also, it typically has higher impurity content as compared to diffusion. In those, basically the plasma is a combination of ions of various kinds and electrons and neutral and atoms and molecules. So ions for which the mass is closer to the mass of the intended ions also pass through the analyzing magnet. So that's why we have higher impurity content in ion implantation. And it is an expensive tool. Like the size of the ion implantation tool is around roughly, I guess, 6 meters by 3 meters by 2 meters. I already talked about their applications. One application is MOSFET, really crucial. The latest technologies are defined by the MOSFETs. And thermal annealing actually results in expansion of these drain and source regions. Like, for example, after ion implantation, you see the depth of these drain and the source regions inside the MOSFETs. The annealing, which is a high temperature process for a particular amount of time, results in expansion of these implanted ions in different directions. So after annealing, we have expanded drain and source regions. And we actually calibrate the annealing process in order to achieve a particular depth of the drain and the source regions. Here are the ion implantation parameters. The crucial parameters are ion species or type. Like for example, for p-type doping, we need for p-type doping of silicon, we need boron ion implantation. For n-type doping of silicon, we need phosphorus ion implantation. Ion energy is the second parameter. It's in the range of 5 kilo electron volts to 10 mega electron volts. Ion energy defines the depth of the ion implantation. The third parameter is implant dose in the range of 10 to the power of 12 to 10 to the power of 16 per centimeter square. It's in per centimeter square because ion implantation impacts the two-dimensional surface of a device. And implant dose defines the carrier concentration of PR n-type dopants in a semiconductor per centimeter cube. There are a couple of really useful softwares for the simulation of ion implantation. One software is SRIM and TRIM software. Here you can define the host material. It could be elemental, or there is also a dictionary of compound semiconductor materials. Then you define the dopant. For example, in this case, I've selected boron. You define the energy, which in this case is 200 kilo electron volts, and then you enter some other parameters and hit input and run trim, and it starts simulating the impact of the ion implantation one by one. So then it finally creates this kind of profile where you see P carrier concentration at a certain target depth. You can see that value over here. In this case, it's around 569 nanometers. 5691 angstrom, or which is 569 nanometers, or 0.5, approximately 0.57 micrometers. But one shortcoming of the SRIM TRIM software is that we cannot enter the dose in SRIM TRIM software. So there is another software, it's called SUSPROI. In SUSPROI software, we define the host material, the target material. We define the dopant or the ion details. And also we define the energy. And the advantage of SUSPROI is that we can also define the dose, which in this case is 10 to the power of 15 per centimeter square. So after simulation, we see these kind of profiles where here we have the P carrier concentration at 6000 angstroms, or approximately 600 nanometers. Also in this software, we can also see electronic stopping and nuclear stopping. As already discussed, that boron is a lighter material, so we would observe more electronic stopping as compared to nuclear stopping in boron ion implantation of silicon. But if you perform arsenic ion implantation, which is a heavier ion, we would observe more nuclear stopping as compared to electronic stopping. And these are really useful softwares. I have posted a couple of videos on these softwares. So if you go to my channel and then click on videos, I have a video on installation and working of SRIM and TRIM software, and then I have another video on installation and working of SUSPROI software for ion implantation. So these videos show like where to download the softwares from, how to install them, and then how to perform the simulation of ion implantation for elemental and compound semiconductors. Really useful stuff. I definitely recommend you to watch these videos and perform the ion implantation simulation using these softwares. Channeling is another concept in ion implantation. So if the incoming ion beam is aligned with the crystallographic axis of the target material, channeling can occur. For example, if the incoming ions they hit the substrate at this angle, they can travel deeper into the substrate material because it encounters less number of collisions. But if the incoming ions hit the target material at this angle, they are going to collide with the host atoms more often, resulting in shallower depth of the ion implantation. So without channeling, we would observe this blue kind of Gaussian distribution where we have shallower distribution of the implanted ions. But with channeling, we would observe this tail effect, where we have distribution over a wider region with channeling. And here in this figure we see the same effect. This figure over here shows the incoming ions, their projected range, projected straggle, lateral straggle, etc. I already discussed that in order to create a plasma, we need to apply voltage to a tube where we have electrodes, and the cathode is in the form of filament. So we keep increasing the voltage, resulting in an increase in the current, and then we arrive at certain beam current, resulting in the emission of electrons striking the neutral atoms and molecules, resulting in a plasma. And here is how we calculate the beam current. I is equal to the dose times charge on electron times area of the wafer divided by time. Now dose is in per centimeter square and area is in centimeter square. They cancel out. The net unit is coulomb per second, which is the unit of current in amps. So the really simple formula to calculate the beam current. We know that we have Gaussian distribution of the implanted ions inside the target materials. The point where we have the peak concentration, the distance from that point to the surface is called the projected range. The distribution of these implanted ions in the direction of the ion implantation is called projected straggle, and the distribution of these carriers perpendicular to the direction of the ion implantation is called lateral straggle, or we can also call it transverse straggle. Here is the carrier concentration as a function of distance inside the target material, which is equal to dose divided by square root of 2 pi times the projected straggle into exponential of minus the distance. This is the projected range once again, whole square divided by 2 the projected straggle. This prefactor over here is also called the peak carrier concentration. The concentration over here at this point. So we have these formulas to calculate these parameters. Here is an example of arsenic ion implantation into silicon at an energy level of 100 kilo electron volts at a dose of 10 to the power of 16 per centimeter square. The peak implanted ions are approximately 10 to the power of 21 at 0.1 micrometers approximately. But the active dopants post annealing are slightly above 10 to the power of 20. So the active divided by the total turns out to be approximately 40%. So the takeaway point is that not all the implanted ions get activated. Some implanted ions get activated and the rest of them are not activated. So the implanted ions have more solubility than the activated dopants inside the target material. Here is the distribution of the implanted ions before annealing, and with annealing the implanted ions gain thermal energy. They start moving in different directions. So we have wider distribution post annealing of the implanted ions, and the carrier concentration versus depth has a slightly different formula after annealing. Here are some figures depicting projected range versus energy for boron, phosphorus and arsenic ion implantation, where the solid lines represents the projected range in silicon and the dashed lines represent the projected range in silicon dioxide. We have another figure over here. Where we have the projected straggle represented by the solid lines, and the lateral straggle represented by the dashed lines as a function of energy in kiloelectron volts. We already discussed that lighter atoms encounter electronic stopping in the host, or we can also call it the target material. The lighter atoms, depending on their energies, have a chance to get backscattered. Some of them get backscattered because of their lighter nature. And because of this backscattering, we kind of see this tailing effect in their profile. So their profile, the profile for lighter dopants is not perfectly Gaussian. It's skewed, and this kind of distribution is called the Pearson-Ford distribution. Here is a table at 100 kiloelectron volts for boron implantation in various materials: silicon, silicon dioxide, silicon nitride, and other materials. And we have the projected range and the projected straggle, which is also the standard deviation for these materials. One key point to note is that the projected range and the projected straggle for boron is approximately the same in silicon and silicon dioxide. Not exactly the same, but approximately the same. We know that in order to achieve drain and source regions in MOSFETs, we need to perform ion implantation. And these drain and source regions have a certain junction depth. This depth can be determined using this formula, which is equal to the projected range plus projected straggle times 2 times natural log into 10 times the peak carrier concentration, which represents the carrier concentration of the drain in the source regions, which are heavily doped regions, divided by the concentration of the bulk region, which is lightly doped. So this is how we determine the junction depth. Now let us focus on an example, a couple of examples on ion implantation. Here is the first example. Consider a silicon wafer with a 200 millimeter diameter. Assume that it is implanted with 100 kiloelectron volts boron ions, and the dose is also given. We are required to determine the projected range, the projected straggle, and which is also called the standard deviation, and the peak carrier concentration. So boron at 100 kiloelectron volts, if we look at these figures, at 100 kiloelectron volts, we get to the boron curve. The projected range is approximately 0.1, 0.2, 0.3 micrometers. And the projected straggle for boron at 100 kiloelectron volts is approximately 0.06 or 0.07 micrometers. So the projected range is 0.3 and the projected straggle is 0.07 micrometers. And then we are required to calculate the peak carrier concentration, which is given by this formula given in one of the previous slides, equal to dose divided by square root of 2 pi times the projected straggle. We already determined the projected straggle. The dose is given in the example over here. Insert the values of these parameters and the peak carrier concentration comes out to be 2.85 10 to the power of 20 per centimeter cube. In this example, we are also required to calculate the beam current for this amount of time. And I already showed you a really simple formula to calculate the beam current given over here. In this example, the dose is given. We know the charge on electron. The area can be calculated from the diameter of the wafer divided by the time in the example is also given, which is 90 seconds. So put in all the values and the beam current comes out to be 2.8 milliamps. Here is another example in which consider this structure where we have a polysilicon, silicon dioxide and p-type silicon substrate, and the thickness of the silicon dioxide is 60 nanometers. We are performing arsenic ion implantation of this structure, and the concentration of the substrate or the bulk region of this region is 10 to the power of 16 per centimeter cube. So we are asked to calculate the peak carrier. We are asked to calculate the dose and energy in order to achieve a peak carrier concentration of 10 to the power of 19 per centimeter cube at this intersection of silicon dioxide and silicon. And we know that the projected range is almost the same in silicon and silicon dioxide, also in polysilicon, because of their same stopping power. So we know the thickness, which is 60 nanometers, turning out to be approximately 0.06 or turning out to be 0.06 micrometers. So we can calculate the energy for this. We are talking about arsenic ion implantation. Look at this figure. The projected range is 0.06, 0.01, 2, 3, 4, 5, 0.06. We come to this point. Approximately 100 kilo electron volts is the required energy. To be more exact, it's 105 kilo electron volts. And for this energy, then we can also calculate the straggle. For this energy for arsenic, the straggle is approximately 0.02 micrometers, or to be more exact, 23 nanometers. Now, in order to calculate the dose, we know the peak concentration is given 10 to the power of 19. We already know about this formula now from the previous slides, is equal to dose divided by this parameter. The dose is unknown, so we reorder this equation, and Q or phi over here represents the dose, is equal to square root of 2 pi times the projected straggle times the peak carrier concentration. So this formula gives us the dose for this configuration. Now part B of this question is asking us to calculate the junction depth of the source and the drain regions, and we have a formula for that as well, for the junction depth, this one. So just put in values into this formula. The junction depth is equal to 145.49 nanometers, but be mindful of the fact that the silicon dioxide has a thickness of 60 nanometers. So deduce that thickness from 145.49. This number minus 60 is equal to 85.49 is the depth of the junction depth of the source and the drain regions inside this structure. That concludes the session for today. I hope this was useful for you. Take care. Adios.